Hello everyone, and welcome to the videos for the cumulative review packet number 8. And remember, if you do better on this test than any previous test, you can count this grade twice in the gradebook. So it could completely replace an old score, which is an excellent opportunity right before final exams. So if I start here with number 1, the directions are to simplify each identity down as far as I possibly can. And so when I look at number 1, if you're ever not sure how to start a problem, I would go through a particular checklist. Ask yourself, can I factor this? Well, nothing's squared, so no. Is there a greatest common factor? No. Can I use common denominators? Well, I have no fractions, so no. And so sometimes the last resort is just replacing everything with sine and cosine. So if I see secant of x, I can really replace that with 1 over cosine of x. And if I see cosine of pi over 2 minus x, I'm going to pull up my identity sheet here, which is the front of your packet. And I'd like to point out to you the cofunction identities, that if you have sine of pi over 2 minus theta, that's cosine. If you have cosine of pi over 2 minus theta, that is really sine. So if I go back to this, if I have cosine of pi over 2 minus x, that's really equal to just sine of x. And technically sine of x over 1. So now if I multiply these two fractions, you end up with sine of x over cosine of x, and sine over cosine is really just tangent of x. So number 1 simplifies to a single trig function, tan of x. Number 2, this was the most missed question on the chapter, cumulative test number 7. So I wanted to make sure there was another one of these on the review packet. Whenever you see a single fraction, remember that the terms on top you could split into two separate fractions, like so. Sine x, cotangent of x, over sine of x, minus 1 over sine of x. What separates terms is a plus or minus sign. So that's why the sine and cotangent are attached and the 1 is not. So the reason this helps me is now I notice that the signs can cross out top and bottom because I'm dividing. So I'm left with cotangent of x minus 1 over sine of x. But 1 over sine of x can be simplified down to be cosecant of x. So this final answer would be cotangent of x minus cosecant of x, because these are not like terms, so I cannot subtract them. They are not squared, so it's not a Pythagorean identity. So that's the most I can do. The difference between numbers 3 to 6 and what we just did is when you see the directions verify, that means that you would like to get this side equal to this side. You never want to move anything from one side to another. You just want to see if one side will somehow equal another. So let's think about our bag of tricks we have for something like number 3. I see squared functions, so maybe the Pythagorean identities will come in handy, but a lot of the time you want to consider algebra stuff first. So can I factor this? It doesn't look like a normal factoring problem, so I ask, can I take out a greatest common factor? Well, it looks like I have no GCF between here and here. Common denominators does not apply because I don't have fractions. So now my resort is to replace identities that I know. So let's turn things into sines and cosines. Let's replace tangent squared of x to be sine squared over cosine squared. Remember, if something is squared or cubed or to the fourth, you can apply the same identity but have to keep the exponents. So tangent of x is really sine squared x over cosine squared x. And that's still being multiplied by cosine squared x, plus cotangent of x can be replaced with cosine squared x over sine squared x, and that's still being multiplied by sine squared x, and we're trying to see if that's going to equal 1. This did help me because when I'm multiplying, the cosine squareds are going to cancel out top and bottom, and the sine squareds are going to cancel out top and bottom. So I'm left with sine squared x plus cosine squared x equals 1. Now this is an identity. I know, and I'm going to underline this, and I'm going to write a note, and this is what you may want to consider doing on your test as well if this comes up. You could write, you're really using a Pythagorean identity, and you know that sine squared x plus cosine squared x is 1, so you've proved that 1 equals 1, check. You always want to end, because it's a proof, with that the left side equals the right side. Number 4, Your goal is to get this side to simplify to be cosecant squared. I would start with the more complicated side and see if you can work it to be this. So when I look at number 4, I'm tempted to want to do the same thing as number 2. Now notice, the denominator on number 2 did not have a plus or minus, so I was able to split it into 2 fractions. However, number 4, when I have adding addition sign or subtraction sign in the denominator, I unfortunately cannot split it into 2 fractions. So I have to go a different resort, or I have to go a different route. And if I notice things are squared again, my eye goes maybe to Pythagorean identities. So I'm going to circle this, and I'm going to look at my identity. So I know from my Pythagorean identities that 1 plus cotangent squared equals cosecant squared. I also know that tangent squared plus 1 equals secant squared. And that might help us in this circumstance. So let me write that over here. I know that tangent squared of x plus 1 equals secant squared of x. So if I'm thinking about replacing this with something, if I move the 1 to the other side, I know that tangent squared x equals secant squared x minus 1. So this can be replaced with just tangent squared x, because I know these are equivalent. And the numerator is still going to be secant squared x. And again, we're trying to get this to be cosecant squared x. Now that I have a trig function over another trig function, a good resort is to change things to sines and cosines so you can prove if this side equals this one. Secant squared is really the same thing as 1 over cosine squared. And tangent squared is really the same thing as sine squared x over cosine squared x. What I've really created, let me write cosecant squared x here, what I've really created is a fraction divided by a fraction. And that is the same as the top fraction multiplied by the reciprocal, cosine squared x over sine squared x. We're still trying to prove that this side's going to equal that. What happens is the cosine squareds cross out, and we're left with 1 over sine squared x. Is 1 over sine squared x equivalent to the cosecant of x? Yes, it is. So my final step would be that cosecant squared of x equals cosecant squared of x. Check. Left side equals right side. Number 5. If I consider my bag of tricks, I think common denominator doesn't apply. I think factoring, specifically GCF. If I look at this first term in the second, I can actually take a GCF out of tangent squared x. And if I do that, I'm left with cosecant squared x minus 1. And we're trying to see if that's going to equal 1. This looks like to me like it could be another Pythagorean identity because I have a squared term. So if I pull up my identity sheet again, I know that 1 plus cotangent squared equals cosecant squared. So I'm going to write that here. 1 plus cotangent squared of x equals cosecant squared of x. And so like the last example, if I would like to get cosecant minus 1 on the same side, I would subtract the 1 over, and I would get that cotangent squared x equals cosecant x squared x minus 1. So I can replace this completely with cotangent squared x, and that is still multiplying tangent squared x, and I'm going to see if this equals 1. Now a lot of you would look at this and say, I already know these are reciprocals, so I know the answer is 1. But for the sake of the proof, what you would need to show is that cotangent is really 1 over tangent squared x. That is technically multiplying tangent squared x. The tangent squareds cancel out, and so you're officially left with 1 equals 1, and that is the end of the proof. Number 6, it looks like we could start with either side. We could try to get this side to equal this one, or we could try to get this side to equal this one. You technically could go either way. I mean, honestly, on any of these at verifying identities, you could go either direction. This one I might even show you both directions, just so you can see them. If I wanted to start with the left side, here's what I would do. I notice that this is really cosine x over 1. So if I wrote this problem with a little bit more space, 1 over cosine x minus cosine x over 1, can that equal sine squared x over cosine of x? Well, I need a common denominator. So this piece already has the common denominator of cosine of x, but this piece needs the cosine of x. So we need to multiply top and bottom by cosine of x, And if I do so, I would get this. 1 over cosine of x minus cosine times cosine, cosine squared x over cosine of x. Does that equal sine squared of x over cosine of x? Again, notice I'm not moving anything to the other side, I'm just simplifying. Now that these have the same denominator, we can combine them together, and we'd have cosine of x on the bottom. On the top, I'd have 1 minus cosine of x. The good news now is that 1 minus cosine of x is an identity. If we look back at the sheet, 1 minus cosine of x, if we move this over, is really equal to sine squared of x. So my final step of my proof here would be replacing this with its identity, which would be sine squared x over cosine x equals sine squared x over cosine of x. Done. Now, if you're interested though, if you wanted to go the other direction, if we wrote the original identity again, which was 1 over cosine of x minus cosine of x, does that equal this? So what if I started with this side instead? What you could do is recognize that this side goes from having a sign to having no signs at all. So we could replace sine squared x with an identity, which is really 1 minus cosine squared of x over cosine of x. And we're seeing this time if we can get this side to be this. So we're actually almost done, because this, remember, if you have a big fraction, you can split it into 1 over cosine x minus cosine squared x over cosine x. And this is really the same as 1 over cosine x. And then when there's two cosine squared on the top and cosine on the bottom, you're just left with 1. So you end up getting each side to be the same either direction. Number 7, we are starting the equations, and again, we've already had exposure to a lot of equations, but these are good because sometimes there's more than one rotation, and it's just more practice with solving with the unit circle. So if I looked at number 7, my goal is to get the tangent function alone. So I would first add 3, and I would get tangent squared x equals 3. And then to get tangent alone, I would take the square root of both sides. And if I do that, I'm left with tangent x equals positive or negative plus or minus root 3. So what we're looking for is all the angles where the tangent value is positive or negative root 3. And that is true at any 60-based angle. So my 4 answers, because we're dealing with positives and negatives, would be pi over 3, 2 pi over 3, 4 pi over 3, and lastly, 5 pi over 3. Number 8 is asking somewhat of the same thing, except look at the angle. This means we're rotating around twice, versus here we're rotating around 1 time. So we didn't have to go all the way around the circle twice. So if we think about what this question is asking first, is we're really asking, where is sine positive 1/2? Or where is sine of theta 1/2? Or where is the y value positive 1/2? Where there's 2 places that's true, either here at pi or here at 5 pi over 6. So instead of setting x equal to these 2 angles, we're rotating twice. So we would set 2x equal to pi over 6 and 5 pi over 6. Now, because this means we're rotating twice, we need to rotate around the unit circle again. And when we do that, we're really adding a coterminal angle, or plus 2 pi, or in this case, because the denominator is 6, that's really 12 pi over 6. So pi over 6 plus the coterminal angle is really 13 pi over 6, and 5 pi plus the coterminal angle is really 17 pi over 6. Now, x is not alone yet, so what we need to do is multiply by the reciprocal of 1/2. And so every fraction is really multiplied by 1/2. And so my final answers with the rotations and the 2 involved would be pi over 12, 5 pi over 12, 13 pi over 12, and lastly, 17 pi over 12. On the next video, I will start with number 9.